In this video, we're going to be looking at rotational dynamics. We're going to be applying Newton's second law for rotating systems. In this case, we're going to start with just systems that rotate only. So there's a fixed axis of rotation. We'll get to stuff that happens when it's both rolling and translating in a little bit. So we've sort of divided these into some categories, the types of problems we can solve. There's the first category, which is what we call static equilibrium, right? The net force is zero, the net torque is zero. And we've looked at some of those. Then the next category is pure translation. These are the kinds of problems that we've solved prior to our rotation unit, right? Net force equals ma, and the acceleration there is really the acceleration of the center of mass, and that's what we're talking about. No net torque, no rotation. And what we're looking at now is this third category where things are rotating and can accelerate rotationally. Their rotational motion can change, but there's no translation. They're not accelerating in a translational manner. The fourth category is where both things can happen. Lots of interesting stuff. We'll get there. So Newton's second law for rotation, very similar to Newton's second law for translation, says net torque equals I alpha. Instead of force, we're talking about torque. Instead of mass, we're talking about moment of inertia or rotational inertia. And instead of translational acceleration, we're talking about angular acceleration. We'll look at single body problems first, and then we'll kind of expand when multiple things are interacting. So if you imagine a wheel, and you say we've got a net force of 1 Newton acting at the rim. This is providing the maximum torque it could provide because it's perpendicular to the r vector. The wheel itself has a mass of 1 kilogram and a radius of 0.5 meters. We're going to call the hub and spoke in the middle massless so that it's just a hoop for a simple moment of inertia calculation. Well, alpha, the angular acceleration of this, should be the net torque divided by the moment of inertia. Well, the torque here is R times that force times the sine of 90 degrees divided by, since it's a hoop, mr squared. We get, move myself out of the way, we can plug in all of our values and we end up with an angular acceleration of -2 radians per second squared. Why negative? Well, that's because clockwise is negative in direction generally. Right? So we can take that information and we can expand on it, right? If we have multi-body problems, you need to still draw the free body diagram or extended free body diagram if it's something that could rotate for each object. We want to pick a consistent positive direction, right? You could always call counterclockwise and all the corresponding linear motion positive, or you can pick the direction of motion as positive. We write out Newton's second law for each of these objects. Some of these may be translational, some of them may be rotational. We get rid of an unknown, and usually that means we take the translational acceleration and the rotational or angular acceleration, and we connect them using this relationship that the tangential or translational acceleration of a point, a distance r from the axis of rotation, is equal to the angular acceleration multiplied by that r. Then we solve a system of simultaneous equations. So when it comes to sines, you can always stick with convention. Counterclockwise is positive. But if everything is moving in the clockwise direction and accelerating in that direction, it may be easier to call that positive in a given problem. So let's look at an example here. We have a pulley with a rope wrapped around it and a package or box hung from it. And it's released from rest. There's no friction in this pulley as before, but the pulley is no longer an ideal massless pulley. It has mass, it has a moment of inertia. So we start out by drawing free body diagrams. The pulley has a force of tension acting on it. It has the force of the axle, and it has, of course, its own weight acting downward. Now, if it's going to rotate around the axle, only one of those forces is going to apply a torque, and we'll get to that. The box has a force of gravity down and a force of tension upward. Right? So we want to pick a direction of motion, and I'm going to call the downward for the box and clockwise for the pulley my positive, even though convention would be the opposite, because that's the direction it's all moving. We did this with Atwood machines as well. Next up, we write Newton's second law equations. Net torque is I alpha. Net force equals ma for the box. The torque on the pulley is just equal to the tension force providing that torque. So FTR, the sine of 90 degrees is 1, so that's gone. In the case of the box, we have the force of gravity downward, which we're calling positive, minus tension force equals ma, right? We want to get rid of one unknown, and we can get rid of either the tension force, A or alpha. Usually we get rid of alpha because it's easy to measure linear acceleration, but sometimes we're interested in that. So I'm going to replace alpha with A divided by R because the angular acceleration of that pulley is the tangential or translational acceleration of a point on the outside divided by R. And we end up with Ft, capital R, is I, the moment of inertia, times alpha R, right? And then we have Fg minus Ft equals ma. Once we have these two equations, we can solve a system of equations. So two equations, two unknowns, that's relatively straightforward. You can use whatever method you like. But here's my example here. I have these two equations. I'm just going to do a substitution in for the moment of inertia of the disk, 1/2 mr squared. A bunch of r terms actually cancel out, right? We have r squared there, we have a 1 over r, we have an r. And so we can combine these two equations to be Fg equals Ft plus ma equals, right, because this is Fg is in that equation, that ends up being 1/2 ma plus ma. These are two different masses. We can solve for the acceleration, which is about 5 meters per second squared. Pretty straightforward. We end up, going back. We can then do all sorts of other things. Once we know the linear acceleration, we could solve a kinematics problem. We could talk about energy, momentum, etc. And this question says the box starts from rest at a height of 2 meters. How long does it take to reach the floor? This is just a kinematics relationship, right? Time is 2 times the distance in the y direction divided by acceleration, and then you take the square root, gives us about 0.9 seconds. If forces and torques are constant, right, then we have a constant angular and linear acceleration, which means we can use our kinematics equations. So what about this, an Atwood machine? Now, before we called an Atwood machine a two-body problem, but if the pulley is not ideal, it's not massless, then we actually need to treat it as a third object. So how are we going to do this? Well, the big change is that instead of saying there's one tension everywhere, we have to acknowledge that if the pulley can actually rotate, not just rotate, but if it has a moment of inertia, if it has its own net torque equation, if the tension on both sides of the pulley was the same as we assumed previously, it would not accelerate. And so we need to say that these two are no longer the same. We need that net torque. So the net torque equals I alpha means that those two tensions cannot be the same, right? If they were the same, the pulley would not accelerate, and that doesn't make any sense. So we'll assume mass 2 is greater than mass 1, and then it will all move to the right and down. We start with free body diagrams. Mass 1 has tension 1 a little bit bigger than its force of gravity. The pulley has force of tension 1 and 2, causing there to be torques. And mass 2 has force of tension 2, which is a little bit less than the force of gravity on object 2. Right? We know that the force of tension 2 must be greater than force of tension 1 because we know it's going to start accelerating and rotating in the clockwise direction. We're going to pick our direction. Again, we could pick whatever we want, but I'm going to call down for mass 2, up for mass 1, and clockwise positive. And then I'm going to write out my Newton's second law equations. Ft1 minus Fg1 equals m1a. The force of tension 2 times r, or the torque provided by tension 2, minus the torque provided by tension 1 equals I alpha. And then finally, force of gravity minus force of tension equals ma for the second mass. What can I do with this? Well, I can eliminate an unknown, right? I'm going to use the alpha equals a over r for the rotating object again. So I'm replacing that alpha with a over r. And now I have in my equations force of tension 1 and 2, the variable, the radius r, and I have the moment of inertia and the linear or translational acceleration. If I put these together, I can start by simplifying force of tension 1 down to being m1 times g plus a. I can plug that in if I want for m1 and m2, or ft1 and ft2. I can replace those, and then I can solve. Right? I'm not going to get a particular answer here. But what is the big idea with all of this? That in some ways, nothing is new. We still know how Newton's second law applies to objects individually. We are learning how it applies to rotating objects, and we're combining that together in a system of equations to solve.